When you hear the word thermodynamics, what do you imagine? Heat, temperature, pressure? Maybe an image of pistons moving inside an engine, or steam hissing out of a kettle. For most people, it is just a handful of technical words that belongs in a classroom or a textbook. But here's the truth. Thermodynamics is not just about the heat and pressure. It's not just a branch of physics. It's the hidden operating systems of the universe. It's the science of transformation, the rules that decide how energy moves, how it changes form, and how it shapes every moment of existence. Every single second, you're living inside thermodynamics. When you breathe in oxygen, your body takes the chemical energy from food and turns it into motion, warmth and thought. When you breathe out, that energy leaves your body in different form. And thermodynamics has quietly guided the entire process. Look around you right now. The light from your screen. That is electrical energy transformed into light and heat. The cool breeze from a fan. That's electrical energy turned into the kinetic energy of moving air. The warm glow of the sun outside your window. That's nuclear energy from the heart of the star, traveling across millions of kilometers only to warm your skin for a few seconds. Thermodynamics does not care whether the system is as tiny as a single cell or as massive as an entire galaxy. The same principles apply everywhere, without exception. It governs the melting of ice in your drink and the swirling of storms of Jupiter. It explains why clouds form in the sky and why black holes slowly evaporate over billions of years. And here is something beautiful. Thermodynamics is not only about describing what is happening, it's about predicting what can and cannot happen. It tells us why your coffee will always cool down on its own, but never heated by itself. It tells us why perpetual motion machines, devices that runs forever without fuel, are not just hard to build, but impossible. It tells us why time itself seems to move in one direction. The most astonishing part, from just a handful of thermodynamic laws, you can explain everything from why your body stays alive to why stars eventually burn out, to the ultimate fate of the entire universe. Think about that. One branch of science, built on only a few core principles, can describe processes from the smallest vibration of an atom to the heat death of the cosmos. That is why thermodynamics isn't boring. It's breathtaking. It's a universal storyteller. Every transformation in nature, every rise and fall, every birth and decay is written in its language. So the next time you hear thermodynamics, don't just think of it as just another chapter in physics. Think of it as the silent, unbreakable code that powers reality itself. Every game has rules. Break them and the game collapses. The universe is no different, and thermodynamics is the rule book it follows without exception. We call them laws, not because humans invented them, but because they have been tested in every imaginable way, from laboratory experiments to the natural process shaping stars and galaxies, and they have never been broken. They are not advice. They are not the theories that might be true. They are the unshakable boundaries of reality. And here is the remarkable thing. There aren't hundreds of them. There are just four deceptively short statements that silently governs every change in the universe, from the flicker of a candle flame to the birth of a star. Let's open this cosmic rulebook, page by page. The first one, the zeroth law, the foundation of temperature. Before we can even talk about energy, we must define what it means for two things to be the same temperature. The zeroth law says, if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then A and C are in thermal equilibrium with each other. It sounds obvious, almost trivial, but without it, thermometers wouldn't work. This law makes temperature a real, measurable property, not just a feeling. It allows us to say with certainty, this is hotter, this is colder, and this is exactly the same. Second one, the first law. The energy cannot be created or destroyed. Energy is eternal. You can't make it from nothing. You can't destroy it into nothing. You can only transform it. Chemical energy in fuel becomes mechanical energy in a working engine. Electrical energy in your phone becomes light, sound, and heat. The first law is the accountant of the universe. It makes sure that the energy balance sheet always stays perfect. No matter what you do, the total amount of energy in the universe today is the same as it was billions of years ago, just spread into different forms. Now the second law, the arrow of time. Here thermodynamics reveals its deepest truth. In any natural process, total entropy of a closed system will never decrease. Entropy, often called disorder, is really the measure of how many different ways a system can be arranged. And nature, left alone, always moves towards states with more possibilities. That's why your hot coffee cools down instead of heating itself up. Why perfume spreads through a room instead of gathering back into the bottle. Why time itself feels like it only moves forward. The second law is why perfection doesn't last and why change is inevitable. Now the third law, the coldest law. Absolute zero, minus 273.15 degrees Celsius, is the lowest possible temperature. The third law says that as a system approaches absolute zero, its entropy or disorder approaches a minimum value. At that temperature, a particle would have the least possible motion allowed by quantum mechanics. But here's the catch. Reaching absolute zero is impossible. The closer you get, the harder it becomes to remove that last trace of energy. It's like chasing the horizon. No matter how far you go, it always stays out of reach. 4 laws, that's all. And yet they decide everything. The birth and death of stars, the cycle of life, the cooling of your tea, the flow of rivers, the ticking of time. Thermodynamics doesn't just describe this process, it controls them. They are not merely rules of heat and work, they are the invisible architecture of reality. If the rules of thermodynamics are the rules of the game, then energy is the player, moving, transforming, and reshaping the universe with every step. Energy is not just one thing, it is the universal currency that exists in many forms. Each one is able to transform into another. Every heartbeat, every lightning strike, every ocean wave, every star's glow, all of it is energy changing its form. Internal energy, the energy hidden inside matter. Every object you see holds energy within it, locked in the motion and arrangement of its particle. This is internal energy, the microscopic jiggling, vibrating and spinning of atoms and molecules. You can't see it directly, but you feel it as temperature. When you heat a pot of water, you are increasing the kinetic energy of billions of molecules, making them move faster until some break free as steam. Kinetic energy, the energy of motion. Anything moving has kinetic energy, from the bullet train racing at 300 km per hour to the slow drifting of a glacier. Kinetic energy can become mother forms in an instant. A hammer striking a nail turns motion into heat and sound. Even the rotation of Earth itself, a vast ball of rock spinning in space, is kinetic energy on a planetary scale. Potential energy, stored possibility. Potential energy is the energy waiting to happen. A stretched bowstring, a raised hammer, water held behind a dam, all store energy due to their position or configuration. When released, this stored energy transforms into motion, heat, or other forms. A waterfall is potential energy in motion, and the electricity generated by it is that same energy, reborn in different form. Then we have chemical energy, nature's battery. Every bond between atoms stores energy. When those bonds break or rearrange, energy is released or absorbed. This is how food powers your body. Chemical bonds in sugars and fats break apart during digestion, releasing energy that your cells use for movement, repair, and thought. It's how fuel like petrol or wood work. The stored chemical energy turns into heat and motion when burned. Then we have electrical energy, the flow of charges. Electricity is simply moving charges, usually electrons. It powers your lights, your devices, your cities. Lightning is the most dramatic example. A raw surge of electrical energy jumping between clouds and grounds, heating the air to 5 times the temperature of the sun's surface. Thermal energy, the energy of heat. Heat is not a substance, it's energy in motion at the particle level. When you place your hand near a fire, the faster moving particles in the hot air transform energy to the slower moving particles in your skin. This is thermal energy in action, a direct expression of the random chaotic motion of matter. Nuclear energy, the power of the atom. Inside the nucleus of every atom lies enormous energy. Nuclear fusion, the combining of atomic nuclei, power of the sun, flooding space with light and heat. Nuclear fission, the splitting of nuclei, drives reactors and tragically nuclear weapons. Both releases millions of times more energy per reaction than chemical process, showing just how much potential is stored in matter itself. And here is the beauty of thermodynamics. All these forms of energy are interchangeable. A falling rock, kinetic energy, hitting the ground creates sound energy, heat energy, and sometimes light. A solar panel turns light energy into electrical energy. A generator transforms kinetic energy from spinning turbines into electricity, which can then become light, heat, or motion again. No matter how energy changes, the first law guarantees it is never lost. But the second law reminds us that every transformation spreads energy out, making it less concentrated and less useful. Energy is not just the fuel of the universe, it is the universe in motion, and understanding it is the first step towards unlocking the beauty and the inevitability of thermodynamics. If energy is the currency of the universe, then entropy is the story of how that currency is spent. Entropy is one of the most misunderstood ideas in science. Many people reduces it to a simple phrase, entropy means disorder. But the truth is richer, deeper, and far more fascinating. In the language of thermodynamics, entropy is a measure of how many different microscopic arrangements are possible for a system while still looking the same on the outside. It is a count of possibilities. The more possibilities there are, the higher the entropy. From order to disorder. Imagine a deck of cards perfectly ordered from ace to king. That's a low entropy. Only one specific arrangement looks like that. Now shuffle the deck. Suddenly the number of possible arrangements skyrockets, and the chance of ever returning to that perfect order by random shuffling is practically zero. That's higher entropy. Not because it's messy, but because there are countless ways for it to be in that state. Nature favors high entropy because there are more ways for things to be discovered than ordered. Drop a cube of sugar into hot tea. At first, the sugar molecules are concentrated in the one place, it is low entropy. But as they dissolve and spread, the number of ways the molecules can be arranged increases dramatically. Entropy rises. The second law has deeper meaning. The second law of thermodynamics says that in any natural process, the total entropy of a closed system will either stay the same or increase. It never decreases. This is why your hot coffee cools, your ice melts, and your perfume spreads out across a room. The concentrated energy and order naturally disperse over time. But here is the mind-bending part. Entropy is not just about the heat and particle, it's about time. In physics, the most fundamental laws are reversible. Run them backward and they still make sense. But the second law gives us a built-in error of time. It tells us which way the future lies, towards higher entropy. It's why you remember yesterday but not tomorrow. Why we age, why stars burn out, and why the universe evolved the way it does. Life and entropy. At first glance, life seems to violate this second law. After all, living organisms build complex, ordered structures, cells, tissues, entire bodies. But life doesn't break the law, it works within it. We create order locally by increasing disorder somewhere else. Your body maintains its internal order by burning food, releasing heat, and dispersing energy into the environment, increasing the overall entropy of the universe. Entropy in the cosmos. On the grandest scale, entropy explains the fate of the universe. As stars burn their fuel, as energy spreads and transforms, the cosmos moves towards a state where energy is evenly distributed, with no temperature difference to drive change. This is the so-called heat death, a universe where nothing happens to because all the energy is spread to change to do work. It's billions of years away, but the second law tells us that it's a natural endpoint of all processes. Entropy isn't just a metaphysics concept, it's a quiet storyteller of the reality. It explains why perfection fades, why systems drift towards randomness, and why the future is never like the past. In the end, entropy is not just about destruction, it's about inevitability. It's the handwriting of time itself, written across everything that exists. We have seen the thermodynamics in your coffee cup, in the engine of a car, in the beating of your heart. But its reach goes far beyond the everyday. It stretches to the very edge of time itself. The laws of thermodynamics don't just govern the small, they rule the grandest scales imaginable. From the birth of stars to the slow cooling of the cosmos, these laws decide not only how the universe works, but where it's headed. The universe as a thermodynamic system. Think of the universe as the ultimate closed system. All the energy that has ever existed is still here, just changing forms. The first law guarantees that no energy is ever lost, but the second law ensures that the energy keeps spreading out, becoming less concentrated, less usable, and less able to do useful work. Every star that shines, every planet that spins, every chemical reaction that burns fuel, all of it moves the universe one tiny step closer to equilibrium, where everything is the same temperature, the same energy level. Stars, life, and entropy. Stars are the nature's great engines, converting mass into energy through nuclear fusion, flooding space with light and heat. Planets orbiting those stars can use that energy to build complexity, to drive weather, to grow forests, to sustain life. But this comes at a cost. The energy that emits is more spread out than the energies they begin with. Entropy always rises, even in the most beautiful creations. Life itself exists in the narrow window between too little energy and too much. We are children of thermodynamic imbalance, alive only because our planet receives concentrated sunlight and radiates back as diffuse heat. When that imbalance fades, so will life. The long future, heat death. Over unimaginable spans of time, stars will burn out, galaxies will grow dark, matter will decay, black holes, the most powerful energy traps in the universe, will slowly evaporate through Hawking radiations. And when they are gone, the universe will be a vast, cold expanse of evenly distributed particles and radiation. This is the so-called the heat death, not fire and explosion, but stillness and silence, no temperature differences, no usable energy, no process to mark the passage of time. The universe will still exist, but it will be eternally unchanging. A different perspective. To some, this is a bleak ending, but there is another way to see it. The universe's entire history, every galaxy, every planet, every heartbeat, is a unique and unrepeatable chapter in the thermodynamic story. The beauty lies in the fleetingness. Stars shine because they will one day fade. Life exists because the universe is not yet in balance. Thermodynamics is not just the science of heat and work. It is the science of beginnings and endings. It is the quiet narrator of the cosmos, guiding it from the first spark to the last whisper. From the melting of an ice cube to the death of star, from the warmth of your hand to the destiny of the universe. Thermodynamics writes the same story on every scale for all time.